At Mach 2, the aerodynamic forces acting on a fighter jet are chaotic and continuous. To model that structural stress in real time, engineers have to chop that continuous physical reality into discrete, quantifiable pieces a flight computer can actually process. We face the exact same hurdle with the invisible. When mapping the electromagnetic flux across a planar sensor array, the continuous field must be quantified to track how the energy propagates. Despite operating on vastly different scales, supersonic airflow versus microscopic magnetic fields, both disciplines are trying to measure and bound continuous spatial geometry. And the problem extends into purely digital environments. When bounding boxes collide in a physics engine, the software has to mathematically prove that two separate geometric planes have intersected. Underneath all three of these systems lies a single algorithmic operation. They are all powered by the 3x3 matrix determinant. This single calculation serves as the primary logical filter through which flight computers and physics engines interpret the physical world. To see how a determinant processes space, we have to strip away the aerodynamics and the electromagnetics down to the bedrock of a basic Cartesian plane. We start by plotting three distinct coordinates, P1, P2, and P3, and connecting them to form a bounded triangle. To translate this shape into data, we extract the x and y values of those three vertices and stack them. This builds the first two columns of a matrix. But matrix determinants require a square grid to resolve. To fulfill that structural requirement, we add a third column comprised entirely of ones, locking the data into a valid 3x3 format. Calculating the determinant of this specific matrix and dividing the result in half gives us the exact bounded area of the triangle, denoted as delta. This equation holds true for any triangle. But the mechanical power of this formula emerges when we push it to its extreme limit. What happens geometrically if the calculated determinant equals exactly 0? An area of 0 means the triangle has collapsed completely. The three spatial coordinates no longer bound any space because they lie perfectly flat along the exact same straight line. This zero determinant outcome is the definitive collinearity condition. It gives a computer a flawless, purely numerical way to test if physical objects align in space. A human can look at a graph and instantly see that alignment. A computer cannot. It has to dismantle the spatial matrices algorithmically to process them. To see how a machine breaks this down, we replace our specific numeric coordinates with a generic grid of variable locations, labeled Aij. The algorithm isolates a single element, let's say the top left, and mathematically ignores all other values in its intersecting row and column. The remaining, untouched elements then snap together to form a smaller secondary 2x2 grid. The determinant of this newly formed 2x2 submatrix is called the minor. To reconstruct the full geometry, the computer calculates the minor for every position. But these individual minors must be scaled with alternating positive and negative signs based on where they originated in the larger grid. This alternating pattern is dictated by position parity. By taking -1 to the power of the row number I plus the column number j, the algorithm calculates the correct structural sign. This finalized, properly signed minor is called the cofactor. Breaking massive spatial coordinates down into structural minors and scaling them precisely with cofactors is exactly how software engines parse heavy geometric workloads. We can now apply this decomposition directly to kinetic aerospace systems. Consider continuous flight trajectory mapping. Flight computers continuously pull three specific telemetry points from tracking radar. They plug those coordinates into the 3x3 matrix, updating the determinant constantly. If that continuous calculation of delta approaches exactly 0, it triggers the collinearity condition. The computer instantly knows the paths have aligned into a straight line, indicating an active collision course. This exact logic also governs aircraft surface design, referencing the aerodynamic boundary meshes we saw earlier. Finite element analysis relies on determinants to instantly calculate the bounded area of thousands of individual structural mesh patches. Those precise area values allow the software to correctly scale localized lift and drag vectors. This same calculation bridges the gap between simple 2D area and 3D force vectors, which is vital for electrical engineering. When modeling magnetic flux passing through a triangular circuit loop, we need more than just the flat area. We need the loop's orientation in three-dimensional space. The 3x3 determinant is the structural basis of the vector cross product. In 3D space, this operation produces a normal vector, a line pointing perfectly perpendicular to the triangle's surface. The length of this vector represents the surface area, while its direction tells the computer which way the loop is facing. This single result provides the magnitude and orientation data required to solve electromagnetic field equations. This brings us to the computational domain. Modern graphics processing units construct entirely digital 3D worlds from massive collections of triangles. To display that world, the GPU has to perform triangle rasterization, the challenge of determining exactly which square pixels on a 2D monitor should light up to represent a 3D shape. The hardware tests a specific pixel's coordinate relative to the edges of the triangle geometry, mapping what are known as barycentric coordinates. By calculating the signed determinant area formed by the pixel and the triangle's vertices, the GPU mathematically proves whether that pixel falls inside or outside the shape's boundary. Game engines apply this identical boundary logic to physics and collision detection. The determinant math proves whether a line of sight or a ray has breached a geometric hitbox. Simply turning your camera in a 3D video game forces the GPU to execute this spatial determinant logic millions of times every single second. When we look back at the fighter jet mesh, the sensor array, and the rasterized screen, they no longer look like isolated systems. Determinants and their cofactor decompositions are not abstract textbook puzzles. They are active engineering tools. From plotting basic Cartesian coordinates to algorithmically dismantling structural matrices, it enforces the rules of geometry. This rigorous geometric logic is the only way a computer can actually process spatial reality. Linear algebra provides the invisible, universal scaffolding that allows human engineers to simulate, measure, and automate the physical world.